All right. Something that we don't really use very often, but it is interesting to think about, is percent ionization. All right. Usually, once we identify how much of a given solution has, or much of a given acid is dissociated, we just say the molar concentration of that dissociated acid. However, it can be helpful to kind of think about the percent ionization to have a better understanding of what's going on. And it's essentially looking at the moles of material that ionized compared to the moles that did not ionize. All right? So let's determine the percent ionization of a 0.2 molar solution of acetic acid. Okay? This is done pretty much the same way. We create our ice table. We start with 0.2 molar here. What's going to be here?
0 and 0.
What's going to be the change here?
Minus x, plus x, and plus x.
Very good. The equilibrium?
0.2. Can we drop that x?
Yeah, we can drop the x, so it's just 0.2 here.
And then x and x.
X and x, very good. Then we are going to solve for x here. All right, so the equilibrium, I will give us a little review here. We've talked about this enough, but it might need a little bit of review. H3O plus times the C2H3O2 minus over the HC2H3O2, the acetic acid, so the acetate ion, hydroxide ion, or hydronium ion, acetate ion, acetic acid. That is the equilibrium expression for this reaction. That is what's going to equal 1.8 times 10 to the minus 5. The equilibrium concentrations for these, according to our ice table, have been identified as x, so x times x squared over 0.2. All right, so x squared over 0.2 times 1.8, so 1.8 times 10 to the minus 5 times 0.2, and then take the square root of that, and you'll get x as 1.9 times 10 to the minus 3. So that is the molar concentration of the hydrogen ion. And if we wanted to find the pH, we could take the negative log of it, right? But that's not what the question is asking. The question is asking what percentage of our acetic acid actually dissociated, right? And so we can take that value, because that is also the amount of acetate ion there is, and divide it by how much we had to start with, which was 0.2. Okay? So I just take my 1.9 times 10 to the minus 3 divided by 0.2 times 100, and then we get 0.95 is the percent ionization. Okay? Now, let's think of what the percent ionization will be if we only have 0.1 molar solution of C2H3O2. Let's go back here really quick. Let's take the negative log of 1.9 times 10 to the minus 3. What'll that give us?
Well, that's the pH, right?
That's right. So if I go up here, I'm going to get this value here, and then I'm going to take the negative log of that value, 2.72. So at a solution that is 0.2 molar, the pH is 2.72, and 0.95% actually ionized. Now let's make some predictions about this next scenario here. 0.1 molar solution of the same acid. What do you think the pH is going to be, higher or lower? And what do you think the percent ionization is going to be, higher or lower?
Let's see. 0.1 is less of it. So I'm going to say that the pH is going to be, there's less acid, pH is going to be higher.
Okay, so you're predicting the pH is going to be higher.
And the percent ionization is going to be less of it ionized.
Okay. So let's take a look-see-loo, right? 1.8 times 10 to the minus 5, we'll use it again. Ice table, filling it out, right? Everything the same as before. Set up our equation, x squared, the concentration of the products over the concentration of reactants. 1.8 times 10 to the minus 5 The pH, 1.3 times 10 to the minus 3, is the hydrogen ion concentration. So the negative log of 1.34 times 10 to the minus 3 equals 2.87.
I was right. I was right.
All right, good job. 2.87. The pH is higher because, again, more hydrogen ion release would make a lower pH, more acidic, right? But this is, again, showing us that less hydrogen ion has been released. The pH is higher. Now, percent ionization, 1.34. How do we find percent ionization?
1.34 divided by the 0.1.
Okay, 1.34 times 10 to the minus third, right?
Yeah, 10 to the minus third.
Divided by 0.1.
Oh, so it's 0.1. So it's 1.34%.
Yeah, times 100, 1.34. Whoops, 1.34% ionization.
Well, I was wrong.
Yeah, so this didn't go down, did it? The percent ionization went up.
Well, why? How did it? If it went up, then why did the pH go down? Doesn't pH? If there's more hydrogen ion, more ionization, shouldn't the pH go down instead of up? Why did the pH go down?
That's a good question. And so what's happening here is more of the material is being ionized, but we put only half as much in to start with.
Oh yeah, okay.
So the actual molecules, if you were to think about it, is going to be, so we didn't write that down there. X here is 1.34 times 10 to the minus third molar dissociated ion. This one over here, the previous slide, 1.9 times 10 to the minus third molar. So that's the hydrogen ion concentration, right? So again, comparing these two, the amount dissociated here, the molarity of the dissociated material, is smaller, and that's why the pH is higher. But a higher percentage actually dissociated. So why is it that a higher percentage actually dissociated? Well, it's because the ratio of water molecules to hydrogen ion, or sorry, to acetic acid molecules is higher in this scenario. So there's more space for that dissociation to occur. Less dissociation ends up occurring altogether because of the lower concentration to start with, but a higher percentage actually dissociates.
That's tricky.
Okay. What's the percent ionization of 0.1 molar HOCl? 3.0 times 10 to the minus 8.
I think I know how to do this pretty easy now. So you just do x squared equals x squared over 0.1 equals 3 times 10 to the minus 8.
So I'll write that down, what you said there. X squared over 0.1 equals 3 times 10 to the minus 8.
And then solving for x tells you the hydrogen ion concentration and also the concentration of the conjugate base in this case.
All right, so 3 times 10 to the minus 8 times 0.1 square root 5.4 times 10 to the minus 5.
And then divide that by 0.1.
All right.
Times by 100.
Okay, 0.054%, 0.055%.
Yeah.
Okay, very good. How about this one here?
I guess you can't just multiply it by 5, can you?
No, you can't.
Because you end up with more, so you got to, well, you can go 3 times 10 to the minus 8 times 0.5.
Okay. Square root of that value.
That's x divided by 0.5 times 100.
All right, 0.024. Yeah, 0.0245. Okay, very good. Here is a solution of an acidic drug. It's 3.5, and we would like to know the equilibrium constant associated with the dissociation of this drug. All right. Let's see if you guys can take a stab at this one, all right?